Today's lecture will be on molarity, the definition of molarity and the different types of problems that you can come across with molarity, from dilution, calculating molarity from dilution, calculating molarity from mass, calculating the moles per ion, and lastly looking at some stoichiometry of some solution reactions. Let's start today with the definition of molarity at the top of the screen there. The amount of solute dissolved per liter of solution. The amount of solute is typically measured in moles and liter of solution. So you end up with units for molarity of moles per liter. That is often abbreviated with the capital M. The capital M is pronounced molar. Now, the two parts of that definition, the solute is the substance being dissolved, the sugar into water, the salt into water, a variety of different examples you could give of solutes. The solvent is your dissolving agent. Most of the time in our first year in organic chemistry class, we are going to use water as our dissolving agent. We have a quick little video here that we're going to show that will further explain and show how this process works. So in this example, the sodium chloride would be your solute, and your solvent would obviously be the water molecules. Notice at the bottom of the screen, you see the polar water molecule with a delta positive at the hydrogen end and the delta negative at the oxygen end. And as you watched that video, you saw that you had the delta negative end of the water molecule being attracted to the positively charged sodium, and the opposite for the chloride and the delta positive end of the water molecule. There are several different types of problems, several different ways we can calculate molarity. The first one that we use most often in class is calculating molarity from dilution. This type of calculation is a calculation that I have to do often to set up solutions or make solutions for your laboratory experiments. An example of this, when I order hydrochloric acid from a chemical company, it typically comes in a concentrated form. Concentrated hydrochloric acid typically has a concentration of 12.0 moles per liter. That is clearly a concentration of an acid that I do not want to give chemistry students. So what I will do is I'll take a small amount of that concentrated acid and dilute it with a large volume of water. So our dilution equation shown on the screen here, M1, the initial molarity, times V1, the initial volume, equals your M2, your new molarity, times your new volume. Our example that we have, we're going to identify our variables. M1 will be my initial concentration, the 12.0 molar. Would be needed to make 3.0 liters. We're going to make that our V2, a 0.50 molar HCl. And so that'll be my M2. So to figure out V2, that's really ultimately what we're going to solve for here. We're going to plug these variables into our equation. And, excuse me, V1, not V2. V1, then we'll have 0.50 molar times V2 of 3.0 liters. We get a V1 here of 0.125 liters, or 125 milliliters. So if I were to get our concentrated acid, I would need 125 milliliters of the 12 molar hydrochloric acid, and then add a significant amount of distilled water to ultimately make 3 liters of a 0.5 molar hydrochloric acid solution. The second type of method for calculating molarity is from mass. We have an example of how to calculate mass, where our question for this problem is, what is the molarity of 34.5 grams of silver nitrate dissolved in 3.0 liters of water? So we need to recognize that we're on the mole map here. We're in the left part of the mole map, where grams So we're going to need to go from grams and convert that into moles and then divide by the volume. Since we're ultimately trying to solve for molarity here, our units of moles per liter is ultimately what we want to try, what we want to solve for. So silver nitrate, first thing we need to do is write a chemical formula for that. We have 34.5 grams. Silver is Ag. Nitrate is a polyatomic ion, NO3. Silver has a +1 charge and nitrate has a -1 charge, so those come together in a 1-to-1 ratio to make a neutral compound. Now we're going to do a one-step mole map problem. We're going to go from the left part of the mole map into the center. So we're going to divide by the molecular mass of AgNO3, which is 143.32 grams per mole of AgNO3. When I do that, my gram unit cancels out with my grams unit. Then I'm going to take this and divide that number by 3.0 liters so that I get unit-wise moles per liter of AgNO3. Mathematically, we get an answer of 0.080 moles per liter of silver nitrate for this second sample problem. Moving on to our third slide here, we have calculating the number of moles per ion. So our sample problem, how many moles of each ion are present in 1.25 liters of a 0.250 molar sodium phosphate solution? First thing we need to do is break sodium phosphate apart into its ions. We have Na3PO4. Okay, when this substance gets placed into water, it does dissolve, and we form 3 sodium ions and 1 phosphate polyatomic ion. Remember the phosphorus and the oxygen, those are bonded together covalently in that polyatomic ion. Therefore, you are not going to have that positive-negative interaction that we saw within this salt crystal with an ionic bond such as sodium and chloride. Moving on. So for each ion, we are trying to solve for moles of each ion. We're going to end up with 2 monorails. The first monorail will give us an answer in moles of sodium. The second monorail will give us an answer in moles of phosphate, both of which are going to start with the 1.25 liters of the Na3PO4. We're starting at the bottom of our mole map. We're going to move from the bottom of the mole map into the center. So we're going to multiply by 0.250 moles per liter of the Na3PO4. Then we're going to do a molar ratio. For the first one, we're going to go from the Na3PO4 to 3 moles of sodium ion. In other words, for every 1 mole of sodium phosphate that dissolves, it's going to produce 3 moles of sodium ion. So that'll be my ratio. 1 Na3PO4 to 3 moles of Na positive. We go ahead and complete that monorail, and we get 0.938 moles of sodium ion. We now have to do the exact same start of a monorail, and ultimately, instead of going to the sodium ions, now in our second monorail, we're going to solve for the phosphate ions and have a 1-to-1 ratio. First 2 steps will look exactly the same. We start with the volume of our solution, the bottom part of our mole map. We're going to multiply by the concentration, 0.250 moles per liter of the sodium phosphate. Then our final step, for every 1 mole of the sodium phosphate, we are going to produce 1 mole of phosphate ions. So we have a 1-to-1 ratio in our second monorail here. We're going to go ahead then and calculate that value as 0.313 moles of phosphate ion. These problems, we could ask you to solve for the moles of each ion, or we could pick one of the 2 ions to ultimately have you solve that problem. The fourth and final problem that we're going to go over in our lecture today is a stoichiometry problem. Let me read this. One way to determine the amount of chloride ion in a water sample is to titrate that sample with standard AgNO3 solution to produce solid AgCl according to this reaction. Then you've got 25 milliliter water sample, requires 27.2 milliliters of 0.104 molar silver nitrate. In such a titration, what is the concentration of chloride in the sample? This is our first time talking about titration in class, so let's look at a basic titration setup. What we're referring to here is a burette, like a device like this, where we're holding it with a ring stand and we have a water sample down below. Our water sample, this is going to be our chloride ion water sample. So we do not know the concentration of the chloride ions in this sample. What we do know is the concentration of the silver nitrate solution that is in the burette. So we add silver nitrate. We recognize that silver nitrate, when it dissolves, it produces a silver ion and a nitrate ion. We have the ability to open up the valve on the burette and slowly add drops of this silver nitrate solution to our chloride water sample, or a water sample containing chloride ions. Once the silver comes into contact with a chloride ion, we're going to form a precipitate. We're going to get a solid AgCl formed at the bottom of our container. So if I were to draw a little bit of red right down here, that would be ultimately the solid AgCl that would form as a result of adding the silver ions to our chloride ions in the water sample. So that's kind of the overview of the experiment that we are conducting here. Now let's look at the data that we received as a result of that experiment. We had a 25 milliliter water sample, 27.2 milliliters of the silver nitrate used. What is the concentration? So ultimately, we're trying to figure out moles per liter of our chloride ion. That's what we're trying to solve for. We're going to start with the volume of silver nitrate, which is measured in milliliters. So our starting point of our monorail, the 27.2 milliliters of silver nitrate. Out of the three pieces of data that you have, starting with the volume that has an associated concentration is your best starting point. As you remember, the concentration is moles per liter because that contains 2 units. That's often a good sign that we're going to use that unit as a conversion factor within the mole map itself. That's why we're starting with the volume, not the concentration. All right, first step, I need to go ahead and convert from milliliters to liters to get myself onto the mole map. Reminder to you, the bottom of the mole map, the volume of the solution measured in liters. So we're now onto the mole map with this first step. Now I'm going to multiply by the concentration in moles per liter of the silver nitrate solution. At this point, units cancel. We've got milliliters and liters to cancel out. We've got moles of silver nitrate. That's where we're going to use the balanced chemical equation that we wrote on the previous slide. This equation right here, we recognize that there is a 1-to-1 ratio between the silver nitrate and the silver ions. So for every 1 mole of silver nitrate, we are going to produce 1 mole of silver ions. Now the next monorail that we're going to use is the second equation that we wrote here. We recognize that for every 1 mole of silver ions, it is going to combine together with 1 mole of chloride ions. So my second ratio from the second chemical equation will be for every 1 mole of silver ions, we are going to produce, or require, 1 mole of chloride ions. At this point now, okay, if we go back and cancel out some of our units, moles of silver nitrate are going to cancel with moles of silver nitrate. Moles of silver are going to cancel with moles of silver, so we end up with just moles of chloride. We're halfway there. We've got moles. Now all we need to do is divide it by the volume of chloride in our water sample, which is the last volume that we're given in the problem, the 25 milliliters. I'm going to go ahead and convert that directly to liters. So I'm going to have 0.0250 liters as my last step in the monorail. That's going to give me the units that I'm trying to achieve, moles per liter of the chloride ion. When I go ahead and do the math and the significant figures, I get 0.113 moles per liter of chloride ion, the concentration of the chloride in our water sample.